Last time we talked about how there are languages that are inside of all that are not inside of reg. For instance, we talked about the language 0 to the n, 1 to the n, which is inside of all because it is some subset of strings. However, it is not inside of reg because it does not have the regular pumping property. So that means that in our picture, where we have all, and down at the bottom we have fin, we know that there's this new category called reg. And inside of fin are things like 0, 1. Inside of reg are things like 0 star, 1 star. And then outside of here are things like 0 to the n, 1 to the n. Now, what we're going to show is that this is divided up into 3 more areas. 1, 2, 3. And that each one of them is distinct from all. I don't want to make this like too much of a mystery that that's what's going to happen. So that's what's going to happen. And let's talk about this one first. But from our perspective right now, we actually don't know whether or not this is going to be all. So let's pretend that all we know is this picture. And we know that 0 to the n, 1 to the n is out here, 0 star, 1 star, and 0, 1. So now let's try to define that set. Let's come up with a way of writing that down. So this next model of defining sets is called a CFG, for Context-Free Grammar. And like before, let's write an example of this, and then let's talk about what the different pieces are. So here's an example that defines 0 to the n, 1 to the n. We write down s goes to epsilon, and then we also write down s goes to 0, s, 1. Now this right here is a context-free grammar, and it defines this language right here, 0 to the n, 1 to the n. Like before, let's talk about what each one of the pieces are. So the first thing to talk about is the structure of this. Each one of these things, this and this, is called a rule. Now it turns out that with context-free grammars there are many, many different terms for all the different pieces. So we call these rules, we call them transitions, we call them productions. Those are each names for each one of these two things. Next, there are names for this spot right here, which is called a variable. It's also called a non-terminal, and it's called a symbol. Now there's one of these, the first one that we mentioned, which is called the start symbol. The start symbol. And on the right-hand side is a string. So this part right here is a string made up of terminals and non-terminals. All right. Now, if we wanted to be formal about what each one of the pieces are, a context-free grammar, G, is made up of 4 pieces: V, sigma, R, and S. V are the variables, and they are some finite set. Sigma is the alphabet, i.e. the terminals, and it's some finite set. S is inside of V. It's the start symbol. Now the last thing is R. So what is R? Well, R are each one of these rules. So what is a rule? A rule is a pair of a V combined with a string made up of v's and sigmas. Okay? And then R is some set of those. Notice that it's not there's not a unique assignment of v to a right-hand side, because notice that there are two right-hand sides for each one of those s's. All right. Now, with this example context-free grammar, how can we show that it is this language? Well, what we'll do is we'll look at an example. So here, let me rewrite it. S goes to epsilon. Now sometimes when we have another rule with the same left-hand side, we put a bar that we pronounce as or, 0, S1. All right. Now, if I wanted to show that 0, 0, 0, 1, 1, 1 is inside of that context-free grammar, here is how I would do it. I would write down S goes to 0, S1, goes to 0, 0, S11, goes to 0, 0, 0, S111, goes to 0, 0, 0, 1, 1, 1. Now what I did right here is I made use of rule A and rule B. Here I used rule B, here I used rule B, here I used rule B, and here I used rule A. Because what I did is I took this S right here and I replaced it with 0, S1. Then I took that S in the middle and replaced it with 0, S1. Then I took that S in the middle and replaced it with 0, S1. Then I took that S in the middle and I replaced it with epsilon. If we would like, we can formally define exactly what this means. So we'll say that some string W is inside of the language of some context-free grammar G if and only if S derives star W. Now what does derive star mean? Derive star means this. So S derives star, whoops, I didn't mean to say S. We want to erase. There are two main rules for derive star. We'll say that W derives star W with no conditions. This is basically the reflexive rule. Next we'll say that W derives star V if W derives U and U derives star V. So this is the transitive rule. So this is reflexive, this is transitive. Okay, now this thing right here of derive, what is that? How does that work? We'll say that U, A, V derives in one step U, W, V if and only if, if, I shouldn't say only if A, comma W is inside of R where U is a string made up of only terminals, A is a variable, W and V are both strings made up of variables and terminals. Okay, so what does this mean? This means that if we have a string where the leftmost variable is A, and if we look in the set of rules, W is one of the things that is on the right-hand side of A, then we can replace it. Now, notice that this derivation relation is not a function. In other words, there are multiple options. So it's like a non-deterministic finite automata in that it is tree-shaped. For instance, with our example, S goes to epsilon or 0, S1, I have the following tree. I could say S either goes to epsilon or it goes to 0s1. And then it goes to 0, 1, or it goes to 0, 0, S1, 1. Then it goes to 0, 0, 1, 1, or it goes to 0, 0, 0, S1, 1. And as you can see, this structure keeps repeating. So this goes to one thing, and then this continues on. So the question is, when is a string inside of this context-free grammar? Well, it's in the context-free grammar if it is one of the leaves of this tree. So this context-free grammar generates this infinite tree, and something is inside the language if it is one of the leaves. So a string is in the language if and only if it is one of the leaves of the derivation tree. All right. So what's next? So we've defined a little example. We've talked about what they can look like. Let's look at some more examples, and in particular, some examples with sort of some, strange features. So the first thing that I want to show is how we can write down context-free grammars that don't have any strings inside of them. For example, suppose that I wrote down this example. S goes to 0, S1, or SS. So now what does the tree of this look like? Well, we start with S, and then we can follow the first rule and get 0s1, or we can follow the second rule and get ss. Then we can follow the first rule here and get 0, 0, s1, 1, or the second rule and get 0, ss1. Here we can follow the first rule and get 0, s1, s, or the second rule and get SSS. So notice that in each one of these cases, the right-hand side includes an S. There's no way to remove an S, and so what happens is it turns out that this tree has no leaves. And since it has no leaves, that means that this tree has no strings inside of it. This context-free grammar is empty. That's interesting. Let's look at other examples. So one thing that's interesting about context-free grammars is that we might like to know what the relationship between context-free grammars and DFAs are. So DFAs and context-free grammars. What's the connection? Well, we know that there are things inside of context-free grammars that are not inside of DFAs. For example, we know that 0 to the n, 1 to the n is inside of context-free grammars, but not inside of DFAs. But what about in the other direction? Is everything inside of a DFA inside of a context-free grammar? Well, let's look at a little example. So suppose that we had this machine. So we start here, which is the accepting state. Let's call that state A. And then on a 0, we'll go here. And then on a 0, we'll stay here. On a 1, we'll go there, and this is state B. And over here, we'll loop on a 1. So what this machine does is it says, does the thing end in a 1? Or is it empty? So the way that we can represent this as a context-free grammar is the following. Our start state will be A, and then A has a rule that says that A goes to epsilon, or A goes to 1A, or it goes to 0B. and then B goes to 0B or 1A. Now let's derive a string with this ContextFree grammar and see what happens. So let's do 0 goes to 1, sorry, A goes to 1A, goes to 1A, goes to 110B, goes to 1100B, goes to 11001A, goes to 11001. If we label each one of these rules, this is, let's call this one F, G, H, I, J. Here we used rule G, then we used rule G, then we used rule H, then we used rule I, then we used rule J, then we used rule F. Okay, is this string accepted by this machine? Well, let's follow and see what happens. We get 1, 1, 0, 0, 1. That's accepted. So notice that what I did is I took an arbitrary machine and I generated a ContextFree grammar that did the same thing. Now notice that there's a very predictable structure to this. Here's the way that it works. Our input is a DFA, so we have Q, sigma, Q0, delta, which goes from Q cross sigma arrow Q, and F. And here's the way that it works. Our output is going to be V sigma R S. So V is going to be equal to Q. There's going to be one variable for every state of our DFA. Q0 is going to be S. Then here's what we're going to do next. We're going to describe how to add rules based on what is inside of delta and whatnot. So here's the first rule that we're going to say. We're going to say that Qi will transition to epsilon if Qi is inside of F. Maybe we'll call this QF. So QF will go to epsilon if QF is inside of F. The idea here is that since QF is a accepting state, that means it is okay for it to consume no string. The next rule that we'll add is we'll say that Qi can go to A Qj if delta of Qia equals Qj. The idea behind this one is that if we're in state Qi, we can consume an A and go to Qj, then that means that if you're looking at a variable Qi, you can get to an accepting state, you can get to an accepted string if you saw an A and then a string that would be accepted from Qj. Let me make that a little bit more J-ish. Okay, so what this shows is that DFA is included inside of CFA. And it is a proper inclusion, they're not equal. Sorry, I wrote CFA, but I meant to write CFG. In other words, we now know that our picture is like this. We have all, we have fin, we have reg, and then we have a fuzzy boundary here because we're not sure if it's all, but we definitely have CFG above that. Now just as an aside, we actually don't call this CFG, we call it CFL for the context-free languages. Basically, we want to be a little bit more abstract. We don't want to just refer to it by the way that we write them down, the representation. We want to talk about it as a larger category. All right. Now, what about things like the closure properties of context-free grammars? For instance, suppose I had a context-free grammar A and a context-free grammar B. Could I union them together? Would that be possible? Well, it's actually quite easy to do so. What we do is we create a new context-free grammar where S either goes to A's start state or B's start state. What about concatenation? Well, that's easy too. Our new start state S is going to go to A.S, B.S. The idea here is that we'll have to generate an A and then generate a B. Now, what about intersection? It turns out that this is not possible, but I cannot elaborate on why it's not possible right now. We'll talk about that later. All right. Now, one of the things that is most commonly done with context-free grammars is to use them for producing like specifications for like programming languages and things like that. So let's look at an example context-free grammar for something like math. We'll have our start state called E, and let's have our grammar contain 0, 1, 2, 3. Let's just leave it at that. Who needs more numbers than those? And then also let's have E plus E and E times E. Now suppose that I gave you the following expression. 1 plus 2 times 3. Is that inside of this language? Well, it is. Here's how we can do it. Let's first label these. Let's call this one A, B, C, D, E. Let's call that one F and G. We skipped D. So we'll start off with our start symbol E. And once we start with our start symbol E, let's use the F transition and get to E plus E. Then we'll use so let me move that. Then we'll use the B transition, and we'll get 1 plus E. Okay. Actually, let's write this a little bit differently. Let's just write the 1 right there. The 1. And then over here, we use the G transition, and we'll get E times E. And then there, we'll use the C transition and get 2. And over here, we'll use the D transition and get 3. Now, from this list of transitions, F, B, G, C, D, what we can do is we can reconstruct the original string, because we know that we'll follow F and then B and then G, C, D. Now notice the structure that this would create for us. I mean, G, it generates 2 E's. The first one is removed by a C and the second one is removed by a D. We can actually draw a picture like this, that the whole thing is an F, and an F has 2 pieces. One piece is a B piece, and one piece is a G piece. And the G piece has a C piece and a D piece. Well, this tree right here is very useful for a programming language, because we could turn it into the data structure that says, well, first you do plus, and you do plus on a 1, after doing, and you do a times on a 2 and a 3. This thing right here we call an AST, an abstract syntax tree. Okay, and this thing over here we call a parse tree. And the connection between a parse tree and an abstract syntax tree is very trivial. So we often use context-free grammars to describe programming languages to be able to write programs that manipulate these things. Now, one thing that you might find curious is that it turns out that this language right here actually admits a different parse tree for this example right here. We could do the following. We could instead use rule G first. So E would turn in using rule G to E times E, and then we would use rule F and get E plus E times E. Then we would use rule B and get 1 plus E times E. Then we would use rule C, 1 plus 2 times E. And then we would use rule D, 1 plus 2 times 3. And that would be the following picture. That would be the picture that has a times on the top and a 3 to the left. Then a plus with a 1 and a 2. Now, what that means is that this grammar right here has ambiguous strings. There are strings, such as this one, 1 plus 2 times 3, that admit two different ways of parsing it. Now, typically, for programming languages, we do not want that. We do not want it to be the case that, that there can be multiple different ways of getting the same strings, because we want our programmers to be able to write something like 1 plus 2 times 3 and know whether or not the answer is 9, like in this case, or whether the answer is 7, like in this case. So we want to make it so that there are no ambiguous rules. Now, it turns out that actually context-free grammars, there is no way to turn a context-free grammar like this one into an equivalent context-free grammar that is not ambiguous. And that's actually a very deep result that I can't really explain in detail right now, but it's kind of an interesting thing about context-free grammars. Now, this is a good introduction. We'll talk more about context-free languages next time.